And the thin layer equation is a lot easier to solve than the Navier Stokes equation, not just because it has some missing terms. It basically, the critical thing is actually the pressure term. It reduces the global features of the pressure term to something like external forcing. Right, so if you consider an entire flow field, if you make a perturbation here, it affects the pressure here and affects the pressure here and goes back upstream. So like if you consider a general Navier Stokes equation. But for the thin layer approximation, that's not the case. We know the pressure gradient can only affect in the streamwise direction, and whatever we perturb in the thin layer approximation doesn't actually get propagated through the pressure equation at all. The pressure equation is passive, right? So that's really something really nice about the thin layer approximation. So at the end, we derived the equations for the thin layer approximation. And in this lecture, we are only going to be looking at the incompressible form. So the incompressible form is partial u, partial x plus partial u, partial y equal to 0. That's the equation we've seen a million times. And then the momentum equation is the something looks normal, u times du dx plus v times du dy. That's equal to the pressure term, which through the outer layer of the boundary in which viscous effect is negligible, the pressure equation can be written as UE times, the pressure term can be written as UE times due dx. Right, that's the Lagrangian derivative of the velocity at the edge, which has to balance the pressure gradient because there is no other terms. Okay, and then I have to add on the viscous effect, which is a nu. So this is v, this is nu. It's really hard to distinguish